Hello and welcome to the Masters in Data Science 460 final project titled Maintenance Interval Simulation and Optimization, presented by Zoe Kimple, Loretta Cambron, and Lauren Weatherly. We'll first start out with a team introduction, followed by a literature review, then key terms and the problem overview, followed by methodology and approach, results, and then achievements, limitations, and future optimization. We have 3 members on our team. First is Zoe Kimple, who is an engineer at Midstream Natural Gas Company. Lauren Weatherly is a data scientist at Bank of America, and Loretta Cambron is a data scientist at Crowe.
To give a brief overview of the project before discussing the literature review, the goal of our project was to optimize a maintenance schedule for a compressor. And so what we're really thinking about is trying to balance the downtime that maintenance would cause with any unexpected failure while also maximizing profit. So as might be expected, a lot of the literature in this area was in electrical and mechanical industries. And many of the papers did discuss the trade-off between frequent maintenance, which would of course cause more downtime of the machines, and then the trade-off between that and unexpected machine or part failure. So of course, if you try to fix a machine more frequently, you won't have as frequent unexpected failure, but if you don't do any maintenance on it, then you may have a huge problem with unexpected failure. So that's what we're trying to balance, while of course maximizing profit as well. And then as far as other papers, there were some extensions of the research and also some criticisms. So some of the papers criticized the mathematical rigor of the reliability modeling that was going on. And so a few different parts of the research ended up classifying parts, mechanical parts, based on mean time to failure. And other papers also looked at the factors contributing to failure rate for different parts.
So a few key terms to review. A compressor is a large piece of equipment that moves gas by increasing the pressure. There are 2 different kinds of maintenance activities, the first one being routine maintenance. This is very similar to maintenance activity on your car that's done every 6 months, for example. So it's maintenance that's done on a specific interval. And it's very important because this kind of maintenance prevents failures from occurring by fixing issues before they progress. Corrective maintenance is performed after a failure has occurred. So these are typically much more expensive kinds of maintenance because a piece of equipment has actually failed and usually has to be replaced, as much as 4 times as expensive, which is what we use for our analysis. The failure rate is how often the compressor is failure over a specific time period, and it's represented as lambda. And then the reliability of the compressor is just what percent of the time is the compressor performing when it is supposed to be performing. And this is given by the equation E to the negative lambda, which again is the failure rate, times the time interval you're calculating reliability for. So our methodology and approach were the following 5 steps. First, we formulated our objective formula that addressed the problem of how often should we be doing routine maintenance so that we prevent failures, but we also don't cause too much downtime, which affects our profit. Next, we identified and gathered the relevant data, which came from non-proprietary company data. Next, we looked at the distributions of some of those variables that impacted both revenue and cost so that we could model our simulation. Step 4 was to build out that simulation optimization problem and solve that in Excel. Next, we interpreted the results of how often we should be doing routine maintenance activities. So some of the variables had assumptions with constant values. So first, we assumed that our compressor was always running 24 hours a day, 7 days a week. Revenue was equal to the standard rate of $50 per MMBTU, which is our volume of gas moved. Our cost of routine maintenance was $800. Our corrective maintenance activity was 4 times that, which is $3,200. Downtime for both routine and corrective maintenance was about 12 hours or half of a day. And the most important assumption was that failure occurs on the given failure rate interval. So if the failure rate indicates that you will have a failure every 3 weeks, then we assumed that failure would occur every 3 weeks, except if a preventive maintenance activity or routine maintenance activity had occurred within 3 weeks prior. So we assumed that a preventive maintenance activity would negate any potential upcoming failure within that failure rate interval. Two of our variables followed distributions which were used in our simulation problem. So the first one was our daily gas volume, which followed a normal distribution with a mean of 1,280 MMBTU and a standard deviation of 120 MMBTU. Our failure rate followed a Weibull distribution, which is a very popular distribution that models failure in the reliability engineering space. So the Weibull distribution is very similar to an exponential distribution, as you can see on this picture, and the rate we went with for the simulation was 0.75, which can be seen in red on the distribution there. Our simulated optimization problem was modeled as such. Again, our objective was to maximize our average simulated weekly profit, which was given by the revenue of the average daily gas flow volume, modeled and simulated using the normal distribution, times 7 days, times a rate of $50. The costs associated with maintenance activities were $3,200 if a failure occurred resulting in corrective maintenance, or $800 if routine maintenance occurred. Again, failure was modeled using the Weibull distribution and the parameter failure rate. So for example, a failure rate might indicate that we can expect a failure to occur on our compressor every 3 weeks. We used this to model when failure occurred, except if our routine maintenance interval was shorter and occurred prior to the expected failure, then we assumed that the routine maintenance activity would prevent the failure from actually occurring. This is the same kind of practice in your car of why you take your car to get routine oil changes so that oil is replaced before any sort of catastrophic failure occurs later on. There's also the cost associated though with doing any kind of maintenance, both preventive maintenance or routine maintenance and corrective maintenance. And this is the lost opportunity cost or the downtime of when we're not being paid because the compressor is not running. So this is why we can't do routine maintenance just all the time to prevent any failure. So the cost associated with that is half of a day times the daily simulated gas flow volume times the rate of $50. Again, the objective function here is subject to the routine maintenance interval. The constraints of the problem were that the maintenance interval, routine maintenance interval, had to be both an integer and positive. Since this is a non-linear optimization problem, we ran our simulation from multiple starting points to see what would result in our highest profit. The results of our analysis led us to conclude that routine maintenance should be performed every 2 weeks to maximize our average weekly profit. If we do perform our maintenance every 2 weeks, we can expect that profit to be around $446,000 a week. This was similar to the other maintenance intervals, but was the highest average weekly profit. However, what was not similar among the different maintenance intervals was that if we performed maintenance every 2 weeks, we would expect our number of failures to be only 6 across 6 months, as opposed to 8 through 10 when we delay that maintenance interval. This results in the highest average weekly reliability of 80%. For this reason, we have concluded that routine maintenance should occur every 2 weeks to maximize our average weekly profit.
So to review, first we found our constant variables and assumptions and listed those out. Then we modeled our known distributions and found that we had a normal distribution and a Weibull distribution in some of our variables. Then we maximized profit using simulations based on our prior knowledge of maintenance costs, and then found that profit would be maximized and failure minimized with maintenance scheduled every 2 weeks. Thanks everyone for watching, and we hope to see your comments in the comment section below. Thank you.